Okay, so welcome to the third lecture on lower algebraic K-theory of rings in the K-theory series organized by the Gotham School. Today's speaker is Amit Kuber as usual, and today's topic is elementary matrices, determinant, and K1 of rings. Yeah.
Okay. Thanks, Deepankar, and thanks to all who are here. Yeah, this is definitely an advanced topic, and still seeing around 20 people on the third day. Yeah, that's still something. So let me quickly recall what we did last time. So we saw that Grothendieck group is a functor, which is denoted by K0 for the German word Klasse. So it's a functor from rings to abelian groups, which is defined via this composition of three functors. First of all, the finitely generated projective modules, they form a symmetric monoidal groupoid. The isomorphism classes of which form a set, which with respect to a the direct sum operation give you a commutative monoid, whose group completion is the Grothendieck group of our ring. So the purpose of this was to generalize the notion of dimensions to all finitely generated projective modules over a general ring rather than just over a field. And we saw two important properties, that there is this short exact sequence, this relative K group, then the K group of R, and this is K group of the quotient ring correspondingly. And this relative K group is independent of it is independent of R. Yeah, which means it only depends on the difference between R and R mod I, which is the abelian group I thought of as a ring, possibly without unity. I mean, so this is what we have seen so far, and excision property is an important property which makes it similar to homology. So any questions from previous lecture?
Sir, I have one.
Yeah.
So if in the top left, the diagram that you have rings to symmetric monoidal groupoids.
Yes.
A ring R will give you a category of right projective R modules, right?
Yes.
But you're saying that is a groupoid?
Yeah, we forget about other maps. We only remember the isomorphisms.
But then if you take the associated commutative monoid, then you will get a single element in that.
No. Monoid. So there will be several connected components of the symmetric monoidal groupoid, one for each isomorphism class, and that isomorphism class will correspond to a single element in the commutative monoid.
But then it's not a groupoid, right? When you go from bottom left to bottom right in that diagram, you will identify all the isomorphic objects.
Yes, but direct sum is an operation which jumps between two different connected components.
And then so if you have a category in you have a groupoid in which there are these components that you're saying, then any two of these components are not isomorphic. There's no map between them.
No, there are no maps. We have purposely forgotten about them.
Oh, so you in the groupoids, whatever maps there are, they are isomorphism. That doesn't say that for any two objects there is a. Oh, okay.
Yes. Yeah.
Sorry. Thank you.
Yeah. Okay. So any other questions? Well, in that case, I again have a request. Let me at least see faces of few people. If you can, please switch on your videos. Thanks a lot. All right. So there was one more presentation of K0 that we saw last time. like this commutative monad that we obtain, we can also think of it as the similarity classes of idempotent matrices. Yeah, this we have seen last time. Yeah, they are same as they are in one-to-one correspondence with isomorphism classes of finitely generated projective modules. So idempotent matrices, which are of finite size, they correspond to elements of K0. I mean, before doing the group completion. Now, today, our interest is in slightly different object. So, relevant to Animesh's question, you imagine this groupoid. Yeah, it's spread out. There are multiple things, like there is 0, which is in its own isomorphism class, 0 module. Then you have, let's say, R square, R cube, and the size gets bigger and bigger. And there are multiple other finitely generated projective modules in between. So K0 is trying to measure how much spread it is. Now, today we are going to look at one concept, which is basis K1, and this concept is orthogonal to this spread. Okay, it doesn't care about how much spread you have, but it cares about what happens eventually. As the size gets bigger and bigger and bigger, what happens? Okay, so this is what our goal is. We will try to, like Hyman-Bass tried to capture this particular eventual behavior in the direct limit of the automorphisms of finitely generated projective modules. I will give you the definition in a moment, but the purpose of this is to do determinants, is to define determinants. Now, as you know, for commutative rings, we naturally have determinant map, but for non-commutative rings, we don't. However, if at all we wanted to define determinant for all invertible matrices, yeah, then what will it be? Yeah, so what is the value group for the determinant? And we'll see in some examples, this actually turns out to be the determinant map. So let us begin. So the main name associated with K1, yeah, K1 of rings, most of the work is done by Hyman-Bass. So for K0, it is Grothendieck. For K1, it is Hyman-Bass, and for K2, it is Milner. And so K1 of rings was defined by Hyman-Bass, and I'm going to start with a slightly complicated looking definition, but we will simplify it as we go along. Okay, so I will start with a symmetric monoidal groupoid or category. It doesn't matter whether there are non-isomorphisms in this category. So let S be in here. We will say that translations are faithful in S if for all ST in S, the morphisms, so consider this automorphisms of little s, to automorphisms of S tensor T. Yeah, this is the notation that we use. It's not really the tensor product, but you take an automorphism and you map this automorphism to F tensor, the identity on T. If these morphisms are injective, yeah, I mean, these are group homomorphisms, obviously. So we are saying that if these morphisms are injective for all S and T. Now imagine what we are saying. Yeah, in the case of proj R, the category of finitely generated projective modules. This property is true. If you take a finitely generated projective module P, you consider its automorphism, and now you are taking direct sum with some Q. Then the automorphism of P will give you an automorphism of P direct sum Q. Well, on Q, you can just consider it to be identity. So this property is still satisfied. Okay, so translations are faithful. So this is the translation. So actually the connected components of groupoids, which we were talking about, so it is making a jump from one groupoid to one connected component to another connected component. And the automorphism group here actually embeds, so it becomes bigger. So as the size of our projective module will increase, these automorphism groups will get bigger and bigger. So now Bass's definition of K1 of S is simple. He defined it to be the limit, directed limit. This directed limit is important because the size has to grow of the first homology group of the automorphism group of S Okay, so this is the group homology that we are talking about. A quick statement about how to compute group homology. So you take any free resolution and augment it with Z, any free resolution of Z, of ZG modules, and you augment it with Z in the -1 component. You tensor it with Z as a ZG module, which is a trivial module, and then you compute this. But even if you don't know all those things, the answer is very simple in this case. So the first homology group with coefficients in Z is very simple. It's simply the abelianization of this. Okay, so we simply have to take larger and larger automorphism groups and take its direct limit of the abelianizations. So let us try to see what happens in the case of K1 of R. So K1 of R is now defined as K1 of Projar. Naturally, because translations are faithful, so we will try to simplify this. So this is isomorphic to limit of automorphisms of, so P in Projar. So automorphisms of P and the abelianization. Now, in this direct limit, 2 weeks ago, we saw that there is some cofinal subset. Do you remember what that was? Anybody? Inside projective modules, there is a cofinal subset. Yes, Sheba Singh, you tried to say something. I don't think I could hear you. Okay. Your voice is too low. Anybody else wants to try? If you could hear him or otherwise. Okay, so instead of projective modules, which other monoid you can construct? Free modules, finitely generated free modules. Yeah, so as P is a direct summand, if P is a finitely generated projective module, then it is a direct summand of a finitely generated free module. So therefore, this directed limit is same as directed limit as n belongs to n of automorphisms of Rn, and then take its abelianization. Yeah, because of cofinality. Free modules are cofinal in projective modules. Yeah. So therefore now, well, what is the meaning of automorphism of Rn? Do you know that group? Do we have a simple name for this group? Come on, say something.
GLNR?
Exactly. So limit as n is in n of GLNR, and then take abelianization. However, now you have to remember something. Yeah, abelianization as a functor. Yeah, so you start with, I'm just writing this. So all abelian groups are groups. And from a group, you can construct an abelian group by taking the abelianization. So this is inclusion functor and this is abelianization functor. And we know that the abelianization functor is a left adjoint. Okay, so it's a left adjoint, so therefore it preserves co-limits. So we can take this direct limit inside and then take abelianization. So it will be the abelianization of the direct limit. Okay. Now, can you identify this group? We gave it a name last time. We called it GLR, the infinitary general linear group, and then take its abelianization. So we have a very simple definition, very simple presentation of K1 of R. It is the abelianization of the infinitary general linear group. And this was the original definition. I mean, for symmetric monoidal categories, you you generalize this idea to get this definition of bus. So we simply have to find this. Now, what is it? What is GLRAB? So for that, we have to actually work with some linear algebra. Yeah, so let me define elementary matrices. Yeah, so I believe most of you are in like later parts of your studies, and it's been years after studying linear algebra. But now we have to recall some of the basic techniques of linear algebra, that for given any matrix which is invertible, then you can apply elementary row operations and elementary column operations on it to convert it into a diagonal matrix. Yes, you remember this process? Sorry, not diagonal matrix, at least an upper triangular matrix. So the elementary operations are what we need. So elementary operations, row operations and column operations are, they give the same effect as multiplication by elementary matrices. So we are going to simply define these EIJs with elements in A. Yeah. So it is the group which is generated by this, where A is in R and I is not equal to J. Okay. So this is the collection of matrices. Now note something, that I am not specifying the size of this matrix. The size of this matrix could be any n which is bigger or equal both I and J. Okay. So these elementary matrices, what do they satisfy? So they satisfy some properties. We'll simply list those properties. So EIJ, when I'm writing them, I'm assuming that they have the same size. So this is EIJ, A plus B. All of you know how to these properties and also how to prove these properties. Then the second property is that if we make sure that the rows and columns are not the same, Yeah, so then these matrices actually commute with each other. If I is not equal to L and J is not equal to K, then they commute with each other. Okay, then the third one is if I, J, K are distinct, so for different rings, in order to find K1R, we are actually just going to use Gaussian elimination. Okay, so you will see how that will be done. So if I, J, K are distinct, then we have this particular identity, which is very useful to identify commutators. So EIJ A, EJK B, EIJ in A inverse, EJK A B inverse is nothing but EIK AB. And fourth one is the property, which is again under the same hypothesis that if IJK are distinct, then EIJA, EKI EIJ A inverse and EKI B inverse is equal to EKJ minus BA. So you take the free multiplicative group with these generators and quotient out by these four types of relations, then whatever you get is the group of elementary matrices. If all of them are size n, then we say that the corresponding group is ENR. So these are the elementary matrices. So using these operations, actually we can show that ENR contains all upper triangular matrices. Okay. Well, the answer is because of Gaussian elimination. We can convert we can apply on any elementary, any upper triangular matrix, we can sequentially apply elementary operations, multiply by elements of ENR, and then we get back to identity. Right. So this property is true. Moreover, yeah, like we can also swap two rows, but with a sign change. So these are all determinant preserving morphisms. So therefore, with a sign change, we can do this. So this particular identity is also true. So this matrix 0, IN, minus IN and 0, this matrix is in E2NR. Yeah. So why is it in E2NR? Because we can do this. We can write this as IN minus IN 0, then IN 0. So in this part, while I'm writing this, you can notice that the flexibility in changing size of such matrices is really the key to doing this. If we were in the same, we were working in a fixed size, then this wouldn't be true. Yeah. So you can see that because ENR contains all upper triangular matrices, it similarly it also contains all lower triangular matrices. So therefore, the product of three such is again going to be in the group of elementary matrices. Yeah, but just with a slightly larger size, double size. Well, if we don't want to deal with the size issues, then we might as well define this ER. This ER is same definition as before, that we'll take the direct limit of ENRs. And how is the embedding defined? Well, these are all invertible matrices. So we always pad with zeros on non-diagonal entries, off-diagonal entries, and ones on diagonal entries. So that's how this is the elementary group, or group of elementary matrices. Each element in this group is a finite size elementary matrix. Yeah, but we have just padded it so as to make it look like an infinite matrix. That is the property of direct limits. Okay. So once we know all these things, now what is its connection with this definition of K1? The answer to that is lies in this Whitehead's lemma. So Whitehead said that the derived series of GLR is this. Okay, so what is the meaning of derived series? Basically, I'm saying that ER is the commutator subgroup of GLR, and ER is perfect. Yeah, in other words, the commutator subgroup of GLR is ER, which is a perfect group, which means it is its own commutator subgroup. So as a consequence of Whitehead's lemma, we'll see something about the proof of Whitehead's lemma. So as a consequence, K1 of R is GLR modulo ER. Well, in other words, what can we say? 1 ER GLR K1R 1 is exact in the category of groups. Okay, any questions so far?
Sir,
Yes.
sir, elementary matrix, you mean that ith row is ith row plus lambda times jth row?
Yes, yes.
That's
yes.
the only elementary operation.
Yes.
So you are not allowing the other two, elementary operations?
The swap we are allowing with a sign change.
Ha.
Yeah, so this row specifies that.
Achha.
Like in particular, if you choose n equal to 1, then this is 0, 1, minus 1, 0. So it is swapped with minus sign. And the other operation, which is usually like which you consider in finding out determinant, is multiplication of a row or a column by the same entry.
Yes. Ha.
However, we are not allowing that because we want ER to be all determinant preserving matrices.
Oh, achha, achha. Okay.
Yeah. So only those which preserve determinants, we are considering them here.
Okay. Okay. Thank you.
Yeah. Okay.
Yeah.
Any other questions? Okay. So now we simply have to look at. I mean, we will see what is the proof of this. Well, obviously, let's look at this particular identity first. this commutator is naturally a subgroup of ER, so there is nothing to prove. However, take any elementary matrix. Now look at property 3. Yeah, so this A times B, you think of it as A times 1. And then you can write that matrix as a commutator. So this property 3 is actually the proof of this particular equality. Okay, whereas this one now we have to work a bit. Okay. To show that the commutator subgroup of GLR is actually that. Now, the interesting thing, I mean, we might ask, what about a general invertible matrix A? Well, obviously, A can have, if the determinant is defined, then A can have any arbitrary determinant, which is just an invertible element. However, if the determinant is defined, then determinant of A times determinant of A inverse is 1. And if we can construct a matrix which is precisely this, whose determinant turns out to be 1 because of that very reason, and if we can show that this particular matrix is in the group of elementary matrices, yeah, this will be a lot of help. So see what happens now. I'm just going to write IN, yeah, A, whatever the size of A, yeah, it doesn't matter. Then 0 and IN. Then I minus A inverse 0 I, and this is IN for an appropriate size. Then IN A 0 IN inverse. Sorry. Oh no inverse here. And then 0 minus IN 0. So this is the identity that Whitehead found. Now notice something on the right hand side. This is an upper triangular matrix. This is an upper triangular matrix, lower triangular matrix. And this matrix we have already shown it lies in ER. So therefore the product of all of them lies in ER. So this particular matrix lies in ER. A very beautiful observation which makes everything work. Even though a general matrix, you cannot find any of its presence in the group of elementary matrices, but if you just put them diagonally, then you have this. And as a consequence now, we can show that the commutators, so if A and B are invertible matrices, then we would like to show that AB A inverse B inverse lies inside the group of elementary matrices. However, we cannot show it directly. We can show it in exactly the double size. So this particular matrix now we can write as, very simply observe what we are doing. It looks like cheating, but yeah, this is a beautiful trick. A inverse 0 0 A, and similarly B inverse 0 0 B. Now these two matrices we have just shown they are in ER, and this one is also in ER because of the same reason. Now the multiplication of all of them is this matrix, which is same as, I mean, if you disregard the size, then it is same as AB A inverse B inverse. So therefore, now we have shown the other equality as well. Yeah. So the commutator subgroup of GLR is indeed ER. And we can use this information now. And yeah, of course, I mean, before defining K1 as a group, we have to also describe what is multiplication. Yeah, so what is the group operation? Well, if you take two matrices of same size, then their group operation must be same as GLNR. Right? The quotient, the cosets of GLNR, modulo ER. Yeah, this is our thing. So therefore, it will be multiplication. However, there is a beautiful way of presenting that operation as well. So see what happens. So the class of AB, yeah, this class of AB is same as the class of AB 001. I mean, or I, whatever you prefer, IN. Yeah, this is simply padding. We are just landing in the higher dimension. And now this particular matrix can be written as, you can multiply. We are working inside the quotient. So therefore, you can multiply it with any element of ER. So this particular element is in ER. These square brackets actually denote the class in K1R. Right? So this one will be A00B. So in K1R, the multiplication can either be done like this or just putting those things side by diagonally, side by side. So these are two different ways of computing product. K1R is a multiplicative group, so we compute product using any of these two methods. Okay, so as a functor, yeah, I mean similar to, so well, I should just say, the way I defined it for this, yeah, K1 of S, this is obviously a functor from sim-mon GPD to abelian groups for strict monoidal functors. For rings, yeah, so for rings, how we can define it? So K1 is indeed a functor. From rings, you can go to groups, and from groups you can go to ab. This is the abelianization functor, and this is the GL functor. So GL is a functor. Yeah, if there is a ring homomorphism from R to S, then obviously you have a morphism from GLR to GLS, and then abelianization is also a functor. The composition of them is a functor. So this is a functor which preserves finite products of rings and directed colimits or direct limits. Yeah, same thing as direct limits. Moreover, I mean, this particular thing that we discussed last time, if you remember that GL of R and GL of MNR are identical. The infinitary general linear groups are identical. So therefore, K1 is Morita invariant. This property will be true for all K groups. K1 will be Morita, like all K groups will be Morita invariant. So in particular, K1 of a ring is same as the K1 of the matrix ring of any finite size. Okay, so these are the properties of K1 as functor. Any questions?
Sir, can you explain the this group operation rightmost identity? Yeah, the second equality.
Yes,
I didn't.
Second equality. This one.
Yes, yes.
Yes. So we are working inside cosets of GLR. Right. So this is a normal subgroup. Commutator subgroup is a normal subgroup. So we are talking about cosets. So basically, I can move my element inside the same coset. So I'm simply multiplying by some element of ER. So I'm not leaving the coset and I just get a different representative for that.
Oh, this is inside GLR quotient.
Yes. I mean, group operation on K1. Yeah.
So everything is up to multiplication by elementary matrices.
Yeah. Okay, Vishwanath.
Sir. Sir, in that same line, what is the multiplication of AB? Like if AB are of not the same order, so you are multiplying.
No, you can always make them of same order. If one is, let's say, size 2, like second is size 3. Yeah. You just make it maximum size and then multiply.
Oh, so multiplying that way and taking that class is same as just writing them down in diagonally and taking it class.
Yes.
Oh, it will be more easier then. Okay.
Yeah.
Okay. Thank you.
Okay. So now that we have seen enough theory, let's try to compute some examples. So if R is commutative, then what can we say? Well, in that case, I'm just going to draw some diagram here. So here is our basic short exact sequence. So we have GLR, then K1R, and then 1 and 1 over here. Then at the top, we also know something about SLR. Well, ER is also a subgroup of SLR. Yes, you agree? Because all of the matrices, elementary matrices which we have chosen have determinant 1. So in that case, we can define the corresponding quotient as SK1R. So this SK1R is going to be our analog of the reduced K0. You will see in what sense in a minute. And over here now, we can complete this particular vertical exact sequence, SLR, GLR. If R is commutative, then we can simply map it to R cross, the multiplicative group of units. Yeah, this is R cross. Then over here, also, I mean, well, I should first finish this. So this is 1. And over here, we take this. This is the isomorphism. This is isomorphism. And this exact sequence is, is also there. So if R is commutative, then actually what happens? This particular map is the determinant map. Yeah, the SLR is basically the kernel of the determinant map. And over here, we also have a map in the reverse direction. Well, I should say that explicitly. So R cross is the group of units in R, which is same as GL1R. Correct? 1 cross 1 invertible matrices are nothing but units. And this embeds inside GLR. So therefore, this particular map splits, which transfers to splitting of this map. And therefore, K1R, yeah, so if R is commutative, then K1R is simply SK1R direct sum R cross. All right. So this R cross is always going to be there. So this is the trivial part. whereas SK1 is the non-trivial part. So if you remember what happened in the case of commutative ring for K0, so K0 was R satisfies IBP, invariant basis property in that case, and therefore Z was always a subgroup of K0, and then the non-trivial part we named it as K0 tilde. Here we are calling it SK1. So if R is commutative, then this is always true. Okay. Right. So in particular, now we can talk about the field. So R is a field. Well, I'm going to do something boring over here. Yeah. For a field, first of all, I want to recall what is Gaussian elimination. So if I'm given an invertible matrix, how do I convert it into an upper triangular matrix? Tell me. What happens if my A11 is 0? What do we do?
I think we exchange rows.
Exactly. Thank you, Ananya. So we swap rows until, to get if A11 is non-zero, is 0. But with a sign change. With a sign change in one of the rows. Yeah, so that we don't change the determinant. Yeah, that is an allowed operation. If you remember, 0 ion minus ion 0, that is an allowed operation. So this is the first operation that we do. Then the second operation we do is multiply by E21A. Yeah, I mean, you know what, just below A11 there is A21. So A21 will make 0 by adding to it an appropriate multiple of A11. So add an appropriate multiple of row 1 to row 2 to get A21 is equal to 0. Now, observe something here. Now we are not for a field, everything is very simple, but A11 was not just a non-zero element after first step, but it was a unit. And therefore, and just because it was a unit, we could change any entry A21 to 0, because A21 was divisible by A11. Yes. So this is the important point here. Yeah. So then ultimately you convert it into, like, you continue doing this until you get an upper triangular matrix. Which you convert into, again, a diagonal matrix. You also deal with use the fact that in an upper triangular matrix, the last row contains only one non-zero entry, only one unit, and use that unit to kill off the remaining entries in that column. Now, for a diagonal matrix, now what happens is to let's say this is 3, this is 4, and the 5 is that multiply sequentially by matrices of this kind, 1 1 1, diagonal 1 1 1, then x and x inverse, and then again 1 1 1. And you repeat this until the only non-1 entry is A11. So we have non-zero entries on the diagonal, and you shift them sequentially so that only one entry remains non-zero. One entry remains possibly non-one, non-trivial. And then determinant is equal to A11. Yes. So this is the Gaussian elimination method, very simply speaking. So when we are doing this, then what did we say? If we start, so in particular, if A is a matrix in SLNR, then the result is in is identity, is ion. If we go through this process, then we have converted that matrix in SLNR into identity matrix. And all of these steps are valid multiplications by elementary matrices. Are you getting this point? Yeah. That we are simply multiplying by that, and therefore in this case SLNR is same as ER. So SLR is same as ER. So therefore SK1R turns out to be trivial. So therefore K1 of a field is nothing but F cross. Yes, so therefore K1 of a field, field is the multiplicative group of units. Yeah, I hope that you got the idea. Okay, so more generally, now this is what happened for a field. What can we say about a division ring? Division ring is not commutative, right? So I will say something about that. So non-commutative, or in general, local rings which have a unique two-sided maximal ideal, right? So unique two-sided maximal ideal. So we can say we can still use Gaussian elimination. Yes, Gaussian elimination actually never prevented us, as long as there was one unit in each column and each row. Yeah, so what happens if you start with a matrix? Yeah, I will just say that. Suppose we are considering this particular row or column. Yeah, let us consider this particular row. Then this matrix is invertible. Therefore, when you multiply it with this particular column, then you will get 1. Which means all of these elements cannot be non-invertible. If all of them are not invertible, then they lie in the unique maximal ideal. The unique maximal ideal consists of all non-invertible elements. So they will all lie in that Jacobson radical, and therefore any multiplication is going to land inside the Jacobson radical, but 1 doesn't lie in Jacobson radical. So therefore there must be at least 1 unit in the first row, and you can argue exactly similar way for every row and every column. Yeah, so I will, since each row and each column contains a unit. I hope you understood this idea. Now, what remains? Yes, yeah. What remains now is that we don't necessarily have a determinant map. However, Dieudonné, so this is a French word, a French name. So Dieu in French stands for God and donné is given, so God given. So Dieudonné, who was supervisor of Grothendieck, so he has given determinant map for local rings. Okay. So actually determinant can be defined more generally, not just for commutative rings, but also for non-commutative local rings. And what are the properties? It is a map. So det is a map from GLR. But we don't land inside R cross, the group of units, but we land inside it abelianization. Yeah, so there exists a unique map which is like this, satisfying the following properties. The first property is that obviously determinant of an identity matrix must be 1. Second property is that whenever you multiply by an elementary matrix, yeah, for E in ER, for an elementary matrix, the determinant doesn't change by multiplication. Then the third property is yes. If A belongs to R cross and we multiply a row of A by A, yeah, this is the map that somebody was talking about some time ago. Then determinant to get B, then determinant of B is A bar times determinant of A. What is A bar? It's the corresponding element in the abelianization. It is coset. And fourth property is that determinant of A is same as determinant of A transpose. So Dieudonné showed that there is a unique map which satisfies these 4 properties. So as a consequence, he also showed like of this definition, there is a 5th property which says that determinant map is actually multiplicative. Yeah, and yes, 6th one is that determinant of swap ij, just swap 2 elements, two rows in this is -1 bar determinant of A. If you swap 2 rows, then you will get -1 sign. So these properties are true. Okay, so we haven't still finished the computation of this, but you can already guess for local rings what will happen for K1. I said something over here. Yeah, R cross is GL1R and that embeds inside GLR, correct? So the same property is true even for local rings. Yeah, R cross is still isomorphic to GL1R and you are still embedding inside GLR, and therefore R cross to GLR, now there is a map which restricts to its abelianization. So therefore we have a map R cross AB to GLR, GLR AB, which is K1. In fact, This map is also surjective. Yeah, surjectivity, because SLR is same as ER. Yeah, we saw the same argument that Gaussian elimination still works. And therefore, all determinant 1 matrices are elementary matrices. So SLR and ER are exactly identical. And finally, yeah, what we need is a map in the reverse direction, right? So I will take you back to that particular slide. From GLR to R cross, now we instead of R cross, we have R cross AB, which is the determinant map, abelianization. And you have a map in the reverse direction, and this also splits. This map splits, not this, but this map splits for a local ring. So det map gives a splitting of the above. And therefore, K1R is isomorphic to R cross. So now you can compute it for an for any local ring as well. Now, I want to also point out that for a field, K0 was always Z. It didn't really distinguish between two different fields, but K1 can. Yeah, for two different fields, the multiplicative groups, if they are different, then we are distinguishing between them. Yeah, they are not isomorphic. They are not Morita equivalent. Similarly, for local rings also, K0 was Z. However, this one does distinguish between them. If the abelianizations of their R cross of their multiplicative groups of units are different. Yeah, so K1 tries to differentiate between things which are identified by K0. Well, more generally, I mean, K1 of a Euclidean domain. So this is all linear algebra. Yeah, you do linear algebra or Euclidean domain, you have the Euclidean norm function. So you try to reduce it at every row, and every column must contain a unit. You show that the unit has norm 1, and then using Euclidean division, you try to do Gaussian elimination, and therefore you will get K1 of Euclidean domain is again R cross. It's a commutative ring, so R cross. So SK1 will turn out to be trivial in that case. However, for K1 of a Dedekind domain, yeah, so for Dedekind domain, what can we say? I'm not going to give you any general result over here, but K1 of a Dedekind domain, you can't really repeat the same process. What happens is, in this argument, what we did was consider the ideal generated by elements in a row or elements in a column. But for a Dedekind domain, the ideals are not necessarily principal. Not every ideal is principal. The ideals are generated by size at most 2 elements. They're either principal or generated by at most 2 elements. So therefore, this is generated by images of, obviously you need GL1R, yeah, which is same as R cross, and SL2. So there will be some SL2 matrices, like you try to use Gaussian elimination at 2 cross 2 matrix. Even if the determinant is 1, you cannot move forward to get a diagonal matrix, because the ideals are not necessarily principal. Okay, so the K1R is generated by images of GL1 and SL2, not just GL1. In particular, if F is a number field, is a finite extension of Q, and OF is the ring of integers in F, then Bass, Milner, and Serre, yeah, this is a very celebrated result, shows that K1 of OF is OF cross. Okay, so rings of integers, over there you have this big result. So this SL2R.
Sir, I think you mean
yes.
K1, right? You wrote K2.
Oh yeah, K1. No, K1. Sorry. Yeah. We are not talking about K2 today. Yes, K1 of this. So if you try to study this K1 of Dedekind domain in general, then for SL2R you will encounter something called Menneke symbols. And those Menneke symbols are these matrices A, B, C, D, where AD minus BC is equal to 1. Yeah, these are determinant 1 matrices, but inside K1, C and D don't really matter. They can change. Yeah, so therefore the class of this is called this Menneke symbol generated by 2 elements, and that will be relevant there. Okay, so these are all examples which I wanted to cover. If you are interested in topology, then you might want to have a look at Whitehead torsion. Yeah, so Whitehead was an algebraic topologist, so he has utilized the theory of K1. Yes, like cutting out some trivial part, just like SK1 over group rings, he quotiented out by a trivial part, and whatever remains, that is called the Whitehead group of group G. Yeah, it is K1ZG modulo the group generated by the elements of G itself. So that Whitehead group is important in topology, but I'm not going to talk about that. So, well, going back to the first slide, yeah, we had this particular short exact sequence. Now what we are will try to do is to extend it into a 6-term long exact sequence. For that, we had to describe what is the relative K1. Relative K1 is no different from relative K0. So relative K1. So as before, we start with a two-sided ideal. So that's the triangle notation, two-sided ideal of I. Yes, Mainak?
So you said that for a Dedekind domain, we cannot try and apply the Gaussian elimination, but
we can until it's a 2 cross 2 matrix.
Okay, but what if we are working with a PID? There we can do this, right? I mean,
yeah.
And so is the does the K1 of a PID comes out to be something nicer than this?
I don't know. No, I haven't seen any result in that direction. So I know that for Euclidean domain, we have this. Well, one would expect that it is R cross, but I have never seen that example, that thing.
Okay.
But yeah, it's worth checking. Thanks for the question. I will also check it. Okay, so K1 of Ri so this will be defined as kernel of this map from K1 of DRI. Hopefully you remember the double of a ring along an ideal I. And from here to K1R via the first projection. First projection, sorry, not I to first projection. Okay, so same definition as before. Yeah, nothing changes. But in this case, we have to again figure out what is K1 of Ri in terms of GLRI. So relative Whitehead lemma. So if you remember, then yeah, GLRI is defined to be the kernel of, no, this is not something we discussed last time, but we define it to be this GL R mod I. And this is the corresponding quotient map. So GLR to GLR mod I. And it's, so GLQ, kernel of GLQ is GLR mod, R comma I. This is our definition. Then ERI, and this is defined slightly awkwardly, is the normal subgroup of ER generated by the elementary matrices Eija, where A belongs to I. So we just know it is the normal subgroup generated by such elements. We don't exactly know what it is. So the relative Whitehead lemma actually says that ERI, then ERI is a normal subgroup of GLRI. Well, of course, it was a normal subgroup of ER. It's also a normal subgroup of GLRI and hence of GLR. And GLRI mod ERI is actually the center of GLR modulo ERI. And moreover, ERI is also the commutator subgroup of can be written as commutator subgroup in two different ways. So ER and ERI, and also as GLR and ERI. And as a consequence of this relative Whitehead lemma, therefore K1 of Ri has another description. So it is also isomorphic to GLRI modulo ERI. And the proof is long. I'm not covering the proof. But this is one presentation and this is another presentation of the same group, same relative K1. Okay, and well, using some method called clutching, which in category theoretic language is pullbacks. So using clutching, you can show that there is this long exact sequence. So K1 Ri, K1 R, K1 R mod I. Then this boundary map is obtained by using that clutching construction. Then K0 Ri, K0 R, and K0 R mod I. So this is the long exact sequence. I'm not going to show you the proof. It's extremely long. This is definitely not the time and place. But you sort of follow the ideas that you know and you will get there. However, I want to show you one application of this. So an application of long exact sequence, which I promised at the end of last talk. Yeah, so consider 2z. Yeah, I mean, well, let me say this. I equal to 2z, which is a, normal subgroup of z, which is my ring R. So let us try to compute these different things. So what is K0 of Z? Please help me. Let us do it together. What is K0 of Z?
Z.
Yes. What is K0 of Z mod 2Z? Z mod 2Z?
So field. So again, Z.
Yes, it is again Z. Very good. Then what is K1 of Z? K1 of Z we have seen using Bas-Milner-Serre. It's the ring of integers in a number field. So it is the multiplicative group of units. So that is plus minus 1. Okay. Whatever is K1 Ri, we don't really care about that at the moment. Then what is R mod I? It is again a field. Z mod 2Z is a field. So K1 of that field is the now group of units. Well, which in this case is 1. Okay, and then K0 of Ri to this. This map actually turns out to be isomorphism. So you can conclude what happens over here. Yeah, so K0 of 2Z thought of as a ring without identity. So this is trivial. Yeah, because this is K0 of 2Z is same as K0 of R comma I. More like going a bit ahead and computing the same thing over here. If we are talking about PZ, where P is an odd prime for P prime, odd prime, then we will get something different over here. Yeah, I mean, I'm still not going to care about this particular thing, but and here also we'll get plus or minus 1, but over here we'll get the multiplicative group of units, right? So this is Z, I mean FP, I can say it's FP cross, then K0 of R mod R comma I, and then Z and Z. So using that, you can compute what this is. The image of this, and like you have to compute a lot of things. So K0 of Pz in this case will turn out to be P minus 1 by 2Z. Yeah, because this contains P minus 1 elements. You also have to consider the maps. Yeah, then only you can construct this, but P minus 1 by 2Z. Right, and you can do the same process by using properties of K1 and K0 as functors, that under direct product what happens, and then you can consider general MZ, and you will also get at some place that it's going to be trivial, finite, I mean finite, not otherwise. I remember Dipankar have to finish.
Yeah.
Don't have to say yes. So now, finally, I mean, I will go back to the first slide itself. Here we said that for K0, we had one more interesting property, that is excision. However, K1 doesn't have excision property. So excision fails. For K1. Okay. And how do we check that? Well, for a same ideal, like we can construct two examples of rings. So 1I, R2 and R2 mod I. And this is 1. So these are same. So there exist examples of two different rings and the corresponding quotients by the same isomorphic ideal. The K1 K1 R1I and K1 R2I, they are non-isomorphic. So therefore excision fails. However, like Wasserstein showed that excision holds for K1, i.e. K1Ri doesn't depend on R if and only if I is equal to I square as an ideal. Okay, so this is my stopping point, that for K1 excision fails. However, we have a nice 6-term long exact sequence. Next time, I'm going to show you that this sequence can be extended on the left with 3 more terms and on the right with infinitely many terms. So I will discuss K2 and negative K theory next time. Any questions?
Okay, so if there are
Okay.
none, then let us stop our session today here. As the professor has already said, we'll have another lecture on lower algebraic K theory of rings on K2 and negative K theory. And then this section will be over. Starting next month, we'll be moving on to higher algebraic K theory by Professor Kirta Shankar. You can check out the website. There is a link to higher algebraic K theory and details. This will be a fresh start with Quillian plus construction and Q construction. So you're welcome to check it out. Okay, bye-bye. Thanks for the lecture.